Okay, so last time this is what we see, right? So the C's are here, and then the B's are here, and then so this is obviously 0. This one is a 2 1, a 3 1, a 3 2, and all the way up to AS1, all the way up to BS minus 1 and BS, right? And then here you have AS and AS minus 1. Okay, so you see that we can write the coefficients of the Ranguta method, right, in this form, right? And in particular, we see that summation of Aij, right, j running from 1 to I minus 1 is basically set as Ci in general, right? Not necessarily always true, but it is a common practice that they have Aij is equal to Ci in general. So this is the shortest way of representing a Rankuta method. Right? So we will see a couple of examples. Right, so if you write the Ranguta method, right, right. So if you look at this method, this is the same method we have when we have V2 is equal to half. Right, so this is a if you remember the last example we did, right, when we first derived a Rankuta method by using the Taylor's expansion, right? So we choose B2 as half at once and then B2 as 1 at one point, right, to derive two different methods. So in the method when we have B2 is equal to half, right, so this is how, so your B1 and B2 are half, and C2, sorry, C1 is 0 and obviously always 0. C2, you take it as 1, and then A21, which is so one of them is alpha and one of them is beta in that problem, right? So they are 1 and 1. And so this is one of the simplest examples of how you can interpret the Rankuta method, right? So let us see another popular method, right? So let me write down another example. Okay, so if you define Z1, Z2, Z3 and Z4 like this, right? So then obviously this is going to be a fourth order approach, right? So similar to the way we started defining a higher order Rambuta method, right? So then you can define the method as follows. And yn plus 1, you define it as yn plus 168 Okay, so if you define a Ranguta method like this, then you can see that the expression can be put in the following table as well, right? Okay, so we can represent this as the following table as well, right? So your C naught, sorry, C1 is 0, that's always 0, and C2 is half, 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 right? So, right, so here it is, right? So that is what you have, right? So, and then the C4 is 1. And then your B's are, remember 1 6, you have to multiply it here, so it's 1 6, 2 6, 2 6 and 1 6, right? So that's important. Right? So you have to make sure you have only H here, right? So in that sense, you have to multiply this 1 6 inside the bracket to find out what are the values you have for B1, B2, B3 and B4, right? And then you have AIJs, right, which are the values which you have, right, in here, right, this, so on, right? So that's have 0 0, and then have 0, and then 1. Okay, so this is how we can represent that in the tabular method, right? So the idea here is, if this table is given, you should be able to figure out these values and these formation as well, right? Or vice versa. If this formation and these formations are given, then you should be able to figure out the tabular representation, right? So one way to the other, you should be able to do, right? So from table, you should be able to go for the other formula expression, or if the formula expression is given, you should be able to go back to the tabular expression, right? So this is how these are two different ways of interpreting the the Rankuta method. Right? So now what we are going to do is we are going to see the convergence and stability of the method, right? So before moving further, right? So let me give you a simple example of how the known classical methods can be considered as the Ranguta method as well, right? Right, so you can think of the explicit Euler method, right? So this is yn plus 1 is yn plus h times some kind of a function here, right? So you can see that, right? So here, right, so clearly you know your a11 is 0 here, and then you know your c1 is 0 and b1 is equal to 1 here, right? So because you have only this term here, right? This one is also 1, so there is b1. Obviously a11 is 0 because c1 is always 0, you know, and a11 is 0, and you have only b1, right? So you can write this in this form, right? So explicit Euler method is very simple because it is very basic. So implicit Euler method, let's see how you can interpret the implicit Euler method. Right, so if you look at implicit Euler method, you know this, right? So it is yn plus 1 is equal to yn plus h times f of pn plus 1 comma yn plus 1. This is your implicit Euler method. Okay, so in this case, you know that your function is this, right? So this is your function you are looking for. So you can see this, right? So that is obvious for you because of the notation which we are following so far, right? So this is basically this, right? So okay, right? So you know this. It's because if you look at implicit Euler method, yn plus 1 is equal to yn plus 8 times f of tn plus 1 plus yn plus 1. But tn plus 1 yn plus 1, by using the explicit Euler method, you can represent this as tn plus h, because tn plus 1 is obviously, you know, it is tn plus h, and forget the h. Right? So and then by using the explicit Euler formula, you can write this as in this form, right? So that is clearly you can see the values now, right? So in this case, you know it's C1 is 0 and C2 will be 1 here, right? And then B2 might be B1 is 0 and B2 is 1 and SPA21 is 1. Right, so check this thing. Right, so this is how you can, if a method is given, you can split it out, right? So for simple methods like this, right, you can rewrite that in the regular Ranguta formula, right? Because you know this function has to be written in this kind of a form, right? So z1 t plus h z1 t plus h z2 and things like that. So you know you can start doing this, right? So then you can easily see the pattern, right? So that is how you do this, right? So similarly for the trapezoidal rule also you can do the similar kind of approach, right? So I will leave that as an exercise for you. Okay, or let me do. We have time. So this is your trapezoidal rule. Yn plus 1 is equal to Yn plus h over 2 times f of tn comma yn plus f of tn plus 1 comma plus 1. So this is your trapezoidal rule. Right, so you can easily see this, right? So this is basically, right? So as usual, let's say if you set z1 is equal to yn, right? And then z2 will be equal to yn plus h times f of tn comma z1, right? So that is the formula we use, right? So h plus f time tn comma yn, actually so yn is tn, right? So that is fine. And then you can rewrite this as this, right? So you know this is fine, you don't need to worry, right? So this one is f of tn plus 1 comma yn plus 1. You can always write it as f of tn plus h comma yn plus h times f of tn comma yn, right? By using the explicit Euler method. So basically, you will have this. Okay, so basically you will have this. So your yn plus 1 is equal to yn plus h times, right? So let me write it down. 1/2 f of tn comma z1, because you know when you write the formula, you write in terms of z's, right? So z1 plus there is a 1/2 of, right, f of Tn plus h, right? This is 1/2 coming from here, Tn plus h, and this is Yn plus h times Tn comma Yn is z1, so that is z2, right? So that is z2. So that's all you have, so you can stop there, right? So you have only 2 terms, so you know z1 and z2 is enough, so you write. So now you know the formula, right? Because you know this is how you write, right? So you remember you write Zi as this, right? So Yn plus 8 times summation of j running from 1 to I minus 1 Aij f of Tn plus Cj h plus comma Zj, and then you know Yn plus 1 is equal to this, Yn plus h times summation of j is running from 1 to s bj f of Tn plus Cj comma Zj. Right, so this is how you remember we define the general Rankuta method, right? But we transform the trapezoidal rule, right, as this, right, by using the manipulations we did here or the formations, right, very similar to what they have in Rankuta method development, and we are able to form this, right? So from this, now you know there is only 2, right? I running from 1 to 2, so basically s is 2, right? So when I is equal to 1, right? So this one is z1, right? So that's obvious for you now. Everything else can be formed, right? So your b1 and b2 are going to be half, right? So if I remember correctly, half, right? And c1, so c1 is 0 and c1 is clearly 0, and c2 is obviously 1, right? And then a21 will be 1 here, right? Plus this one here. Okay, so now you can put this in the table if you like, right? So let me squeeze the table here. So you will have 0, 1, a21 is 1, this one is right. So trapezoidal rule, you can interpret this in this table, right? Because the way you manipulate here, right? So this is the Euler, and the Euler method, there is nothing to do there because there is only one term, so not much of work there. So at least in the trapezoidal rule, now you can see that you can actually do the formation work and get the Ranguta formula, right? And so that is why I did this example detail. Right? So this is in this way, for any multi-step method, any linear multi-step method, you can always formulate in this fashion, right? And develop a Ranguta method or the Budger's table, right? For the Ranguta method, right? So this is one good exercise where you see one of your most easiest linear multi-step method transform into a Ranguta formula, right? So then you can see that Ranguta formula is basically another type of a linear multi-step method, right? Right. So now what we are going to do is we are going to focus on the convergence of the method, right? Stability, convergence, and all the other things related to the Ranguta method, right? So that is what we are going to start now. Okay, so convergence and stability and stuff like that, right? So, and convergence and stability of the Ranguta methods. Okay, so let us start from the beginning again, right? Recall how we started the numerical computation of Ranguta method, right? So we see that this is how you started, right? Yn plus 1 is equal to Yn plus h times capital F of Tn comma Yn with h and y0 is basically y0. So this is the method, right, applied to the initial value problem this. Right, so this is how we started, right? So for this kind of an initial value problem, we basically apply this kind of a Ranguta method to solve this, right? So notice that this is also we defined earlier the truncation error for the true solution. We define it as Tn plus 1 y, right? So you know the formula and you know it is of order, right? For the second order method, we see that it is of order 3, right? So depending on the order, you have the truncation error is of order of n to the power certain value, right? So now what we want to define is define right. So let us define a function tau h, right? Sorry, tau of y, right? Which is tau sub n of y, right? Which is 1 upon h times the truncation error for the true solution capital Y. So if we want to show the convergence, right? right? So now we want to show the convergence of the Ranguta method, right? So if you want to show the Ranguta method, you know, basically you want to show tau and y goes to 0 as h goes to infinity. That means the error goes to 0 as h goes to 0, right? So that is how you show the convergence in this kind of numerical method. But however, you know that the truncation error is this minus this, and you divide by it, so you get this, right? So that you can easily see by looking at the truncation error, right? So yn plus 1 minus capital Yn, right? Minus of h times this, right? So when you divide everything by h, right? So this is what you have here. And remember, this capital F depends on where the small f is defined, right? Because capital F is basically a composition or convolution of functions small f, right? So that is why I put tn comma ytn comma h and then colon f, because capital F depends on hf as well. So that is important, because when we are talking about limits, that might also play a role there. So let's keep that in that way. And now because of this, right? And so because of this, okay. So here you see that this tau and y is this, right? But whenever tau and y goes to 0, right? You know that this goes to 0, so this whole thing will goes to 0. Right? If the whole thing goes to 0, that means limit of this should be equal to limit of this, and there is no h here, right? So then limit of, you can say the limit of this, right? So you know that, so from this limit of this and limit of this should be equal, so that this will be 0, right? So when it goes to infinity, so limit of this will be equal to limit of this, and this is the definition for y prime. You all know that, right? So from A level, that is how you define y prime. So basically, you know that if the the truncation error you define here converges, then this one is true, and vice versa, right? So and vice versa as well, right? So if this goes to this, then this goes to this, so this goes to 0, so this goes to 0, right? So vice versa is also true. Okay, so then you know this is what you need to have for convergence, right? So that is y prime of t, so f of t comma capital Y of t. So if you want to prove convergence, or if you want to show the method is convergent, then you need to have capital F converges to small f as it goes to 0. Right? So this is what you want to have. So what you do is you take the difference right? And you make the difference goes to 0. That is how you show that if you want to show this goes to this, then you know the difference between these two must be 0 as it goes to 0. Right? So and y is b minus. So you define delta H as the supremum of the absolute value of the difference between yf small f and capital F, right, for the computed value. Right, so in that case, right, so you know so then clearly you know for convergence. So clearly you know for the convergence of this method, you should have delta H goes to 0 as H goes to 0. That is what you want to show. Right? Right. So this is basically called consistent. Right. So this is called the consistency condition for the one-step method, which I just defined. Right. For the one-step method, this. Okay. So this is called the consistency condition for the one-step method. Right. So if you recall what we learned in the linear multi-step method, there also you can see that we did something like this, right? So we see Tn plus 1 over h, limit h goes to 0, this if and only if consistent, right? So we have this kind of a definition for consistency in linear multi-step methods when we studied linear multi-step method, right? So the same kind of condition is been developed here for the Rangutta methods as well, right? So you can easily see that you started with tau n goes to 0, right? So tau n you defined as Tn plus 1 over h. So it's basically almost the same idea what you have in linear multi-step method, but because the formation is different, right? So everything looks different, but base idea is same. So you know that in linear multi-step method also, you see that consistency and zero stability are the necessary and sufficient condition for the convergence of the method. Okay. So here also, you can see that in order to show the convergence, we need to have consistency first. And so that is one of the conditions we can develop. Right. So now to do further, right? So basically, if you think of this as an error, right? So you can reformulate the formula or the method by including the error term in that, right? Because you always know, if you want to prove convergence, you have to make sure the error is minimized or error should goes to zero. That is the idea. So you can include this error term here, right? Right. So you rewrite the method when the method is applied for the real solution. Right. So when you replace the approximation by the real solution, right, that is when you define the truncation error, right? So you know that you define the truncation error by looking at the real solution applied to the method, right? So real solution substituted in the method. Right? So that is the right word, substituted in the method. So in that case, by including the error, right? So you can rewrite the formula or the method as this, right? Yn plus t and so on and so on. Right? So in this case, you obviously know, right? So you have to prove the convergence, right? So again, to prove the convergence, one of the conditions we can have is Lipschitz condition, right? So you learn about that when we talk about Euler method at first, right? We use Lipschitz condition and prove the convergence, and also we did not use Lipschitz condition in the linear multi-step method, but in Euler method we use Lipschitz condition, right? So we are going to revisit the Lipschitz condition part here, right? And then if we assume that this big F satisfies some kind of a Lipschitz condition, right? Then we can try to develop some kind of a convergence result, right? So that is one of the primary ways to develop convergence result. So in the next class, that is what we are going to do. We are going to see what will happen when the capital F function satisfies some Lipschitz condition, right? And also we will later on talk about the rate of convergence by looking at the error term again, right? So you know that if the error term is order of h, then you know the rate of convergence is h, and things like that you see in the earlier method, right? Especially the Euler method and the other methods. And similarly, we are going to develop same kind of results for these Ranguta methods as well, right? So about those, we will talk about that on Friday class, right? So I will stop here and then continue on Friday.